Good day, ladies and gentlemen, and welcome to the Quasi Cyberseminar conference call. My name is Carl, and I will be your coordinator for today. At this time, all participants are in a listen-only mode, and we will be facilitating a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press star followed by 0, and the coordinator will be happy to assist you. I would now like to turn the presentation over to your host for today's call, Mr. John Duncan. Please proceed, sir.
Thanks, Carl. Well, welcome everyone to today's Cyberseminar by Witold Krajewski. The topic is validation of hydrologic remote sensing. As you know, this is the third semester of this education and outreach lecture series. This semester we're doing vision papers. These are small travel grants awarded to just over a dozen groups to develop their vision for where hydrologic research should go in the next decade. If you have any problems today from the technical end of things, please send me a chat in that chat box, as people are getting accustomed to, or dial star 1 to talk to an operator. As Carl mentioned, your lines are all muted to cut down on background noise. After today's presentation, if you have any feedback, please let me know. You can do that by sending an email to commanager@tawazi.org. If you have catastrophic internet problems or WebEx problems today, as the case may be, you can download this presentation from our website, www.tawazi.org. There's a PDF file there, VTech's presentation, that you can go through. And just let me know if we need to announce page slide numbers and that kind of thing. Just wanted to plug the next few cyber seminars coming up. There's one this Thursday. All of these are at 3 p.m. Eastern Time. Thursdays is on bridging river basin scales and processes. That's going to be a talk given by Dave Duwally of Penn State University. The next one will be next week on watersheds and urbanization by Bill Johnson out of the University of Utah. And then November 10th, Dave Gochis from NCAR will be giving a talk on advancing coupled land-atmosphere prediction. All of this, the complete calendar and links to the draft papers and presentations, is all on our website. Before I introduce today's speaker, I should mention that he developed this talk in Microsoft PowerPoint 2003, and for whatever reason there were some technical glitches in getting that file format loaded correctly into WebEx. So he's got some really amazing graphics, and I hope they come through okay. We've really been working hard the last couple days to make sure that they all go through. But my apologies in advance if any of them don't come out. Dr. Witold Krajewski is the Rose and Joseph Summers Professor of Water Resources Engineering at the University of Iowa. He received his master's and PhD in Environmental Engineering and Water Resources Systems from Warsaw University of Technology in Poland. He's published over 100 papers in refereed journals. He's a fellow of the American Meteorological Society and the American Geophysical Union. His scientific interests concern multiple aspects of rainfall measuring, modeling, forecasting, and estimation of radar using satellite remote sensing. His current research focuses on modeling uncertainty of multi-sensor rainfall estimation at a range of temporal and spatial scales. So with that background, I'm pleased to introduce to you Witold Krajewski. And Witek, you should now have control of the presentation.
Okay, thank you very much, John, and welcome everybody. We are having a hydrologic day here in Iowa City. It's raining hard, and we could be collecting data. I would like to propose to you a concept of hydrologic remote sensing observatory. Back in June, a group of researchers gathered together in Iowa City here, and we were discussing issues related to validation of remote sensing. And without going into details of what is that I understand by validation, I will just say that very quickly in our workshop we decided to expand on this concept and discuss remote sensing in a broader context. And through our discussions we developed this vision of establishing a community facility designed and operated by hydrologic community, by Quasi, which we term Hydrologic Remote Sensing Observatory. We have no doubts that such remote sensing observatory would advance hydrologic science, would foster interactions between hydrology and related sciences, and it would support future developments of remote sensing useful for hydrology. Well, this is our vision. We envision this Hydrologic Remote Sensing Observatory as a piece of land that is well instrumented with both in situ as well as remote sensors, sophisticated cutting-edge technology sensors, dense networks that are in situ, mobile platforms based on trucks and aircraft, and just all sorts of useful gadgets. This would be a place that would collect some core data that would be useful for a variety of remote sensing related studies. This would also be a place where groups of researchers could come to conduct focused and specialized experiments that are not possible on problems that are not possible to be investigated with the core data alone. So now I will try to justify this concept and hope that at the end of the talk you will all support this vision. Remote sensing is here to stay, and so this talk is not to justify remote sensing, but to justify establishing a remote sensing observatory. So for remote sensing, clearly international programs and initiatives such as GWEX, which is Global Energy and Water Experiment, TAP for Prediction of Engaged Basins, and GOES, which is Global Earth Observing System of Systems. All those programs and initiatives rely on space-based remote sensing to fulfill their missions. So there is no problem, there. Also, scientifically, many would agree that remote sensing offers the best and perhaps, the only avenue to link different spatial and temporal dynamics of hydrologic processes across a wide range of scales in a way to make the information contained in remote sensing useful for prediction of hydrologic processes. So now the structure that we adopted to justify this concept of establishing Hydrologic Remote Sensing Observatory is based on 4 questions. We selected 4 questions from many such questions that could be formulated. You see here the short version of these questions. They range from monitoring the landscape to building hydrologic theories to improving predictive capabilities of hydrologic models to quantification of uncertainty of remote sensing based products, hydrologic products. So now we use these 4 questions to show that if we had a hydrologic remote sensing observatory, not only that we could answer these questions more effectively, but in the process we would save a lot of time and hopefully learn many other things that our group could not anticipate. So now I will walk you through these questions one by one and try to emphasize the potential benefits of having an observatory. So question number 1, it relates to monitoring landscape change. And this text below that you can see is the full form of the question as we include it in our paper, which, by the way, today, I hope that you will all read and send us some comments on before we submit it for formal review. So you can read faster than I can. So clearly there is a question not only on remote sensing abilities to monitor landscape changes, but especially to facilitate investigations that can translate those changes into hydrologic effects. Okay, so the specific example that we selected to address this question is monitoring land use from space. And urbanization is an example that is perhaps extreme, but certainly helps to make a point. There is no denying that we have this capability to monitor large scale, all the way to global, of land use. But again, just monitoring that is not enough. We have to understand the consequences of changing land use. Land is a precious resource, as all those of you who are, homeowners in expensive urban areas know. And so now let's take a closer look at this capability. Here is an example from NASA, developed based on land information system, which until recently existed with resolution of about a quarter degree, so roughly 20 to 30 kilometers or so. And the latest version has the resolution of 1 kilometer. Here I have an example of latent heat flux map for southeastern U.S., where you can see the effect of resolution only between this quarter degree and 5 kilometer of such data. And clearly you can see in the bottom panel here that there are many urban areas that do not even, show up on the upper panel. For Iowa City, where I sit, even 5 kilometer resolution would be questionable, because basically this would be 1 pixel. And areas like DC here, it is clear that to understand what is going on, you really need that 1 kilometer or higher resolution. But again, it's not about the resolution. It is more about the effects of these different land uses and their changes. And if you look here at the outputs of latent heat flux calculations from different land use models, and I list 3 well-known models here. I assume that you know what the acronyms stand for. You can see that these predictions are all over the place. There are some similarities, of course, but there are some strong disagreements here. So formation are viable with high resolution, but having the ability of translating this information into a hydrologically useful product. So clearly there is some work that remains for us to be done. Here the urban area near Houston clearly demonstrates that these different models show perhaps different things. Now it is again not about urban areas only. One can give powerful examples of agricultural applications where different ag practices lead to major consequences in terms of hydrologic processes, yet identifying these different practices from remote sensing, especially from space-borne remote sensing, even with the highest resolution, is not an easy task. So here the justification for the Hydrologic Remote Sensing Observatory is that having such an observatory, we could collect 2. This one is about linking, scales, scaling, studies. Clearly, remote sensing provides an avenue that is perhaps the best avenue for us, to follow. But before we proceed, we better understand what is that these remote sensors, really measure, and how are these measurements really relevant to the processes that are of interest, to us. So here, to address this question, we selected an example of scaling of soil moisture. Soil moisture is an important process, a key hydrologic state variable that controls partitioning of water mass falling on the surface, as well as partitioning of energy. So there is no arguing with the importance of soil moisture, and within the hydrologic remote sensing, community, there is a strong community that has been trying to understand the capabilities of remote sensing in quantifying soil moisture, and made many advances. Doing this via field experiments for the past 20 years or so. Now, in Iowa, 2 years ago, there was another of these experiments, and here, hot off the press, some results of data analysis, data collected during the experiment that took place in Iowa, and here, Ames, Iowa. The results are from Princeton, and they show you an example of the capabilities, that we have between aircraft-based remote sensing and how that can later link to satellite-based remote sensing. And I will try to make a case that we also should not neglect going, the other way. So here is an example of some scaling analysis. I don't really want to dwell on this, although there are some very interesting, points that I would like, to discuss, at length. But this is not my main point. My main point is as follows. Let's take a look at what happens now at a pixel, scale. So clearly these are very high resolution, pixels. But here is an example of long-term 8 years of effort by Brian Hornbuckle. What Brian had, he had a sensor with even higher, resolution, L-band radiometer, and he placed this sensor in a flat as a table field of corn in Michigan, uniform, soils. You cannot find, a better setup for if you want to get good results. So this is the setup. You can see that a footprint is just few square meters. Brian followed a growing season of corn, and here is what he learned. Very briefly, 4 panels here: rainfall in the top panel, soil moisture as observed by in situ, well-calibrated, well-maintained instruments. The behavior that you can see here is well understood. This is what we expect: a nice response to a rainfall, impulse, very low amplitude diurnal changes. And here is what some additional measurements showed. So here we have infrared vegetation, or temperature of the canopy top, the green line, the soil under the canopy, and so the soil surface, and then the top layer of the soil shown, in blue. And you can see here that also there is a strong diurnal, cycle here, a little bit disturbed by that rainfall, event. And in the bottom, you have radiometric measurements. And you can see here, and this is my only point that I want to make about this. You can consult Brian for more details. You can read his paper just published in Water Resources Research. But here I want to show that going from the bottom panel to the second from the top is not an easy task unless you include the information that is obtained through this panel, measuring all these, temperatures that are relevant, to the problem. And this is without looking at the effects of geometry, viewing angle, and all sorts of, things, like this. So the point is that even at a very small pixel level, unless you have a host of other information, you may not be able to interpret remote sensing, signal in the proper way. Again, details are in Brian's, paper. It took Brian many years to come up with a nice example, basically one season of tracking the important, changes in the dynamics of soil moisture in the presence of vegetation, again, as simple as corn. It would hopefully take us less than that. So let me move on to question number 3. I will come back to that point that I was just making before. Let's take a look at another example of assimilating remotely sensed information into models for hydrologic predictions. There is no arguing that by combining models and data, one can get improvements in predictions. Kalman formulated a problem like this for linear dynamic systems, 40+ years ago, building on some work of others. So we all accept, this. However, because we have a much more difficult, and complex, situation of nonlinear interactions, multiple, scales because of sense heterogeneities, and so forth, for us to use the same concept and to use to realize the benefits of using this concept, we have a long way to go. We have to understand the uncertainties involved, and we have to understand the effects of different, model structures, and we have to make sure that we represent the right processes in a correct way, and so forth. So here is another example then. Land-atmosphere energy exchange, and we go back to Oklahoma now to another of these soil moisture experiments. If you look here at the top panel, you see the fluxes derived from GOES, the stationary satellite data, with fairly coarse 5-kilometer resolution. So here I call it, coarse. Before I called it, high resolution. But GOES provides data with high temporal frequency every 30 minutes or so, so one can learn the dynamics of these, processes at these scales. But now if we take 2 pixels, both showing a similar, level of flux on the average at that scale level, and if we look inside with another, sensor that allows us to disaggregate this flux into very high resolution information, we can see a wealth of variability. We can see that within each of these pixels we have a range of changes of factor of 2 easily, really more like factor of 5 or so. If you take another look at this, and if you consider that in each of these 2 pixels there was a flux tower, and therefore you could calculate the fluxes from these, well, I'll call them, in situ data. And then if you consider the variability that we all see with the fact that what the tower instrument orientation depends on the wind direction and magnitude. If you consider this, then it becomes, very quickly very obvious that comparing point observations with aerial observations, great care. And again, an argument for an observatory where hopefully in a pixel like this we would have many, perhaps many towers and perhaps many other sensors and instruments that would allow us to make more sense out of this variability, to look at different effects and different causes ranging from topography to vegetation type to all sorts of other factors. So let me now continue back to Iowa. This is from 2002, another similar experiment, now using the atmosphere land exchange inverse or ALEXI model that combines remote sensing information within a certain modeling framework. If you take this and if you then add another feature to obtain disaggregated ALEXI, so basically you incorporate remote sensing information from another sensors that has a higher resolution, you can obtain an image of latent heat flags like the one shown on the right. Just to give you a rough idea of the scale here, the resolution here is about 30 meters, but these gray panels here, these are on the scale of a farmyard. So not just a farmhouse, but a farmyard, so a few hundred, yards, or so. Now, if you look at the same image scene, the same situation, with another sensor, a completely independent, sensor, you don't see exactly, the same, thing, because you are not looking exactly, the same way. But if you have here in this location, you have an elastic scanning, horizontally scanning LiDAR that collects data at very high resolution, but the data are now from above the canopy level, then you will see the panels on the left. There is no full-time correspondence, here, sometime, shift, but clearly you can see that there is a very good, similarity here. The red field happens to be a cornfield, and this is, soybeans, and you may not see certain, details here in the LiDAR field just because the atmosphere, the atmospheric effects, the fact that you are looking at water vapor in the atmosphere already smears some of the details, here that may be present at the land, surface. So again, an example of an argument calling for an observatory, because in an observatory we could have LiDARs that would operate, if not all the time, then certainly whenever we need them, whenever researchers call for their operations. And LiDAR is just an example of a sophisticated, sensor, here, but there are, many other sensors that Hydrologic remote sensing observatory could be home to. So let me move on to question number 4. This is about validation, the original subject of our workshop, but more importantly, quantification of uncertainty. So I understand validation here as quantification of uncertainty of hydrologic products that are based on remote sensing. And here the example is of remote sensing of rainfall, both radar and satellite. And it's not just about satellite rainfall estimation. NEXRAT is a remote sensor, big time. However, there is no such a thing as a validation framework for NEXRAT. Certainly nothing worth discussing, here. On the other hand, NASA, for their CHIM mission, recognized the importance of validation and spent many millions of dollars for this purpose, still with mixed results. So now I will show you a few very simple results of the benefits that we could realize from having an observatory, remote sensing observatory for rainfall. Take a quick look here. We have a vertical profile of radar reflectivity, and I'm showing you this just to show the incredibly rich structure of rainfall fields. So these data were collected by a vertically pointing radar, and you can see both horizontal as well as vertical variability of very high order here. You can also see region. You can see the next-rad, beams for different elevations. In this particular case, next-rad radar was located very close, some 80 kilometers from where the data were collected. So that's why this lowest, beam is fairly low. But you can imagine that as you are moving away from the radar, you are looking at higher and higher places in the rainfall, all the way to the region that is not highly relevant to what happens near the surface, which is where our interest is. So now, if we had an observatory, we would need not only these vertically pointing radars, but all sorts of other instruments, from dense networks of rain gauges to dystrometers to small scanning radars, and maybe not one, but many, maybe a network, maybe even a LiDAR to look at rainfall. Why not? And collectively, then we could really learn a lot about what is going on. And all this is necessary in view of that very high variability that I was just sharing with you. Now, from this technology-rich, high-resolution view over an area to an example of a very small but yet important, experiment. Again, this is an example of what a single investigator can do that we could do much more if we had an observatory. Greg Chach, a colleague of mine, when he was in Oklahoma, conducted this very simple experiment, collected some 16 tipping bucket, rain gauges, and compared them. They are all subject to the same rainfall, and therefore the results collected by these different gauges should be the same. Well, if you compare one against the 16, you can get an estimate of the errors of tipping bucket gauges at a point, granted, but you can do this a function of temporal scale, integration scale. This is for two interpolation methods, or two methods of processing, the basic, data, and I don't want to dwell too much on such a simple sensor as a tipping bucket, but I want to show, this result, because even though the tipping bucket gauges have been in use for 30 years, nobody has done this, before. So here we have a quantification of random error due to tipping bucket, gauges. Well, we can take this concept, a little bit, further, and we can ask a question. Okay, so how many gauges? What kind of a network? What kind of a density would we need to really evaluate or validate or quantify uncertainty of products as those given by NextRad, for example? So here is an answer. Actually, our British colleagues, they recognize that this is a problem. They posed this question and they answered this question. They designed and implemented a few years ago 2 or 3 clusters of rain gauges over 2 by 2 kilometer areas, and they only had money for the red dots, 8 gauges, and then later I calculated that if rainfall correlation function is such that the correlation distance is about 5 kilometers, which it is for highly convective rainfall, then the error with those 8 gauges would be about 8%, and if you keep on adding, gauges, if you double them, this is 17 gauges that you see here, you can bring the error to about, 5%, or so. So this is a doable experiment. If the rainfall is better behaving, like, here where the correlation function is about, 15 kilometers, you can bring this error down to about 3%. If you have reference errors as small as these, then you really can talk about quantification of uncertainty of rainfall. This is not the only way. There are other ways to go around this problem, but I don't want to focus on that right now. So, are there such as the British example in the U.S.? Well, not really. The only two that I know of is, again, due to Greg Jack, who established this Oklahoma Piconet, some 25 double-gauge sites at the Oklahoma City airport. And then there is a network here in Iowa City, but not exactly as dense as this one. And what can we learn from those? Well, we can learn things that we really didn't know. Amazingly, we didn't know, before. So this is an example from Iowa, where we could quantify based on these specialized rain gauge networks. We could quantify the correlation function of rainfall for different, situations. And indeed, you can see here that the correlation distance is for Iowa rain is around 10 to 15 kilometers or so. And of course, we could never guide on operational networks developed and operated by the National Weather Service, USGS, and other agencies. So if we want to learn, we're on our own, and we have to get organized. Now, what are the benefits of remote sensing, observatory? Clearly, I try to make a case to show you, a few examples that if we get organized and we come together and we develop, these sites, we can gather information that takes a long time for us as individuals, to gather. Took 8 years for Brian Hornbuckle, took 5 years for Greg, took more than 5 years for our group here at Iowa, and it's a slow going. We could do, much better. It's been taking 20 years for the soil moisture remote sensing, community with these seasonal experiments, and I strongly believe that we can do better. So, what are the benefits here? Well, they range from improvement of our basic, knowledge to developing new technologies and theories, to understanding scale interactions, to rigorous evaluation and comparisons of models and algorithms. How can you compare two different, models if you cannot evaluate any one of them? Okay, so how would this work now? So functionality of remote sensing observatories. Well, the principles have to be very similar to those guiding hydrologic observatories, because in our view, hydrologic observatories are a bigger concept than remote sensing observatories. Remote sensing observatories provide a focus for hydrologic observatories. But they could be smaller because, as I was showing you these few examples, actually by studying an area that is as small as 5 by 5 kilometers, you can have plenty of challenges, but also you can have plenty of learning. We can foresee that it would be because we do want and we do need to link into these global scales that are made possible by space-borne remote sensing. So we have to have that link all the way from very small scale processes, few square meters, all the way to the coarser, resolution of remote sensors. Some other principles, here, we strongly believe that one can really learn if one collects information that is relevant to many different processes at once, because we simply do not understand enough the interactions between these different processes acting at different, scales, both in space and time, to be making, these choices and then just, hope, for the best that the choices that we made are, good enough. Finally, we need to high redundancy of sensors so that when one fails, the community still, receives, data. We need to automate, as much as possible because as much as there is value in graduate students walking through muddy, fields, there is also a benefit of them doing data analysis. And something that is not here on my slide, but something as important as these other items, is that the data would be distributed to the community right away in what I call near real time with very small delay, so there wouldn't be sitting on the data until the first publication. So this is out. This concept it's outdated. Now, we believe as a group that Quasi is the best opportunity for hydrologic remote sensing observatories, largely because it is independent of NASA and NOAA and other agencies, yet it would be helping them, big time. But we think that as much as it is important for NASA and NOAA and other agencies to be involved and help establish and perhaps instrument the observatory, it is also prudent for credibility of all that it is the hydrologic community, the science community that operates this facility. We also think, and there is something very important, that such a facility would increase our standing within the, there are many other communities, biologists and geologists and oceanographers that use, remote sensing, and many struggle with the same basic, questions of interpretation and validation. And if we take a big step towards addressing, these questions, then I think we will benefit in many other ways. The cost, actually, if you look at the paper, there is 10 million, so I just added, 2 million just to be covered. So again, we see this as a bargain. But this is not, a proposal. If we were to write a proposal, we can justify these numbers. Actually, they were not. We went through an exercise as a group, and based on what we collectively knew about the cost of these different, instruments, this is how we came up with these numbers. The facility would be operated by about 10 to 15 scientists, engineers, and technicians. And it would be a great fun to have it. So with this, I would like to thank all of you for your time, for paying attention, and for your future support of the Hydrologic Remote Sensing Observatory. Thank you.
Well, thanks, Vitek. I appreciate your presentation and the effort that you and your team put into this. There's already a question in the chat box, so if you'd like to ask a question, you can do that via the chat box or by hitting *1 on your phone to get into the audio queue. Vita, can you see that question from Praveen Kumar?
Yes, I can. Okay. Yeah, I cannot answer all such questions at this moment. I do believe that this particular, question could be addressed through development of a new class of models, because at this point, we just speculate. We know that there are some controls, there that would be difficult for us, to observe, but the remote sensing observatory would not necessarily be limited to surface, observations, could have, subsurface observations, and then by developing, models that would link, surface and subsurface would at least, give us, a shot. Would this be the ultimate, solution? I don't know.
Okay. More questions? Type a chat message or *1 on your phone.
Once again, ladies and gentlemen, if you wish to ask a question, please key *1 on your touch-tone telephone. If your question has been answered or you wish to withdraw your question, please key * followed by 2, and the questions will be taken in order received.
Well, it's certainly an interesting idea and concept that you fleshed out fairly well. I appreciate the effort that went into it. A comment that I have that you might want to respond to is the issue of co-location with a remote sensing observatory that's presumably a much smaller scale than what we're talking about for these hydrologic observatories. And you're saying that co-location isn't necessary but preferred, and I would definitely think that it's preferred just because so many other measurements that would be long-term in the same place for the continuous record over space and time would be so much more beneficial to trying to advance all of these questions that you posed here in your talk.
Yeah. Well, that's true. On the other hand, if the community likes the concept, I think that the hydrologic remote sensing community is ready and will be ready before the rest of the community is ready for hydrologic observatories. Okay, that is a speculation, as well. But the hydrologic observatory concept remains somewhat, vague. And this is my personal reading of what is going on in the community. And this is despite the fact that some 20+ groups are already working on proposals. I still, sense that there is a great deal of uncertainty, surrounding, that vision. On the other hand, for remote sensing, if we put together the collective experience and knowledge of that soil moisture remote sensing, community with rainfall remote sensing, community, and add, a couple more, then we could have, given the money, we could have a facility, tomorrow. Well, that's an exaggeration, of course, but we could be up and going, very soon. So the point here is that we could have a much smaller prototype somewhere, and it doesn't have to wait for our decision and spin up of the HO. But we could test certain ideas, and not necessarily even the scientific ideas, but even the operational, ideas. What type of, sensors, how we could, operate them. What else do we need? How do we disseminate the data? And so forth. So that could be done offline, meaning somewhere. And then when we are ready always do this.
Yeah, I agree with you. There's another question from Penn State in the chat box there.
Yes, actually, we discussed this idea. So mobile here would be in a general sense. Like for example, we talked about moving a facility like this from one place to another, but not on a monthly basis, but on the basis of when we are satisfied with our learning. So first we could start with a simple homogeneous, if such a thing exists, situation in hydrology, and then after 2 or 3 years, when we think that oh yeah, we understand everything, there is nothing new to be learned there, well, let's move on to a more complex terrain, and we take our toys and move them. So that's one type of mobility. But one can also make an argument, and I can certainly make this argument for rainfall, that it is collecting large samples that is critical. That if you collect 1 or 2 events, there is just no way that you can learn certain things. And so you have to stay put until your sample is large enough. And how large is large? Well, for some things perhaps we know the answer, and for others we don't. So we debated, between these two extremes. Clearly, some of the sensors would be mobile in any case.
Okay, we've got just a couple minutes until the top of the hour wrap up. Carl, are there any more questions in the queue?
At this time, we do not have any questions.
So I guess last chance for questions, and then if you think of any after we end here today, there will be a discussion forum up online shortly. We had some network connection problems earlier today, and I wasn't able to get up in advance of today's talk, but it will be there shortly. Last chance.
Thank you all again.
Well, thank you, Vitek, and thank you, and your team for all the effort that you put into this.
Thank you.
Well, thanks a lot, everybody, and the next one of these will be this Thursday at 3 p.m. Eastern, a talk by Dave Duwally. Have a good afternoon.
Thank you for your participation in today's conference. This concludes the presentation. You may now disconnect. Good day, everyone.